thought I would go over a couple of items from page 17, the data regression. This is also just a really good review of all of the Excel that we've been working on. So on page 17 in your lab manual, if you look at the instructions there, we're going to do some data regression, and there's quite a few things that each of our models is going to use. So I thought we'll just start looking at these. I'm going to start in my first example. I'm going to use problem number 3. And you can see in problem number 3 that we're given year 2005, 2006, 2007, and 2008. And you may remember from a previous math course that sometimes to get the model right, that we may let the year that we started be a previous, like 2000 or 1990. So I'm going to say that the year since is going to be 2000. So then if you look over, I have already created here the model. So I've got year since 2000. So 2005 would be 5, 2006, 6, and then 7 and 8. The amount spent in millions comes down and is directly from the chart that we were given. The first thing that we're asked to do is to calculate the average rate of change. And you may remember that this first cell in the average rate of change column is always blank. You don't have an average rate of change because remember, you need 2 different data points to get your average rate of change. So I'm going to double click on this cell so you can see the formula that I used. And remember, it's the difference in the y values, or here the amount spent in millions, divided by the difference in the x values, or the time that's passed, the years. Be very careful with your parentheses there. When you hit enter, you can see the 3 values that I generate for the average rate of change just by double clicking down. Ratios is another application that you might remember from a previous math course. And again, what you want to think about with ratios is that that first cell in the column again is going to be blank. So when I double click on my formula cell here, you can see that for ratios it's really just the second y value divided by the first y value. We're talking about the growth there. So when I hit enter and you see that the ratios there, 1.218, 1.103, 1.1024, those are the ratios that we get from one year to the next. Second order differences are basically something that we use really to predict quadratic functions, and I wanted to make sure that on this one I spoke about that because interestingly enough, these second order differences that we're seeing here are exactly the same. Second order differences are the differences in the average rate of change, and because here we've got sequential years, we don't need to make it look like slope. We can just say C27 minus C26, and if you notice in this cell I have C28 minus C27, and they are the same value, which would lead us, we might think that the best representation would be a quadratic function. I wanted to just go through that for a second, but let's go ahead and I'm going to highlight my first 2 columns, the original data. I'm going to insert a scatter plot. One of the things that's interesting about this scatter plot is that we definitely see a curve unfolding here. So let's go ahead, right click, add a trend line, and if I move this text box out of the way, one of the things that we could insert if we wanted to, the default is linear. So I could display a linear trend line. Remember the r squared value, the closer that r squared value is to 1, the better the fit. So I'm going to go ahead and show you. There's my linear trend line. I'm just going to pull that out of the way for a second. I'm going to right click again, add another trend line. This time I think I'll try exponential. Okay, so I've got two trend lines there. Neither of those are very good fits. Let's keep going. This time, how about I try a power trend line? The power gives me a little bit better R-squared value. This time I think I'll try a polynomial, order 2. That would be our quadratic. And notice what happens here. With the quadratic trend line, wow, I get a really impressive R-squared value. And one of the things that I'm noticing is that, in fact, that second order difference, because it is the same value there, that makes sense. One of the things I want you to think about is, as this, if we pick the quadratic as our best model, some people do, will the amount spent in millions, it looks like, well, what's happened is we've already hit the top of our model, and then that thing would continue to decrease. Well, that might be a model for a while, but it probably wouldn't be a model forever, because certainly we aren't going to have negative money spent on Halloween. But, some people would say, oh, that's definitely the one, and other people would say, absolutely not. You can, argue one way or the other for that for a relative period of time anyway. I'm going to click one more, and I'm going to, let's see if I can, actually I may need to insert another scatter plot. I may have too many things going on that one. And let's look at one more trend line. How about this time we look at a logarithmic? Let's see what that one looks like. Okay, so that's not a bad model either. Not great. Obviously, the quadratic model mathematically is the best model. But for the circumstance of what we're thinking about, this money spent at Halloween, we have some other possibilities. For the sake of making a prediction, let's go ahead and use the logarithmic model. So what I'm going to do in my column here, F, is that I'm going to go ahead and type in the logarithmic prediction. So if I'm going to type in that prediction, I know that what I need to do is start with an equal symbol. Some people may try to copy and paste that formula. I am simply going to type it in pretty quickly, 39.513. Remember to insert your multiplication sign. Oops. 39.513. Multiply ln, and you can see it pops up. Double click, and then there we know that we're going to access our cell from the input column. Close your parentheses, subtract 13.521, hit enter. So what happens in this column where we're seeing our predictions, we can see that the values that we're getting are in fact pretty close to the ones that were our actual data. If we wanted to determine our value in 2010, which is what I believe this question is asking, we would type in 10, and it gives us approximately the value of 77.46 million. That logarithmic model that we're looking at up here is kind of a nice model just because, it is still increasing, but certainly not as fast as it was increasing at the beginning. The other models maybe hold some merit to you, but more than anything for this problem, I really just wanted to go through and talk about the different things that you might want to investigate. The last thing that we're going to do in problem 3 is it says use GoalSeek to find the year when $70 million will be spent. So let's go ahead and if we want, let's add a dummy row, and let's add a dummy row of 7.5. If we add a dummy row of 7.5, you can see that immediately it gives us a value of 66.0938. I'm going to click in that cell, outlines the cell, data, what if, goal seek. The value that we're going for is 70 million, so we just type in 70. The cell that we're going to change is always the input cell. That tells us that at approximately, in the 9th year, after the 8th year has passed, in that 9th year, approaching 9 years, is when we would hit $70 million with our logarithmic prediction. Okay, for those of you who this was a lot of review for, take from it what you will. For those of you who are still learning from this, look at it as just another way to be able to go through and see what we have going on. I will upload this spreadsheet so that you will be able to manipulate it as well.